Okay, I guess we can get going. If people are late, they'll straggle in. As we know, Facebook operates one of the largest networks in the world. And yesterday we heard Omar talk about the next generation fabric that they're deploying. And so to talk about some of the provisioning and testing of the fabric, we have Lalita and Ashik. Thank you.
Hello, everyone. My name is Lalita Damaraju from Facebook. Today, I'll be presenting along with my colleague, Ashik Ratnani, on large-scale operations for our next-gen fabric and fabric hardware. Why is this topic relevant? When we plan to introduce a new hardware into our data center, there are two most critical questions with the new design. First, is the design ready to be manufactured at scale? And second, once we roll in the data center, what's the strategy to deploy, maintain, and operate this piece of hardware? So our presentations today are catered along these two questions. So the agenda is hardware testing for new platforms and FPOS deployment infra. So what do we want to achieve with hardware testing? We want to validate hardware platforms with high confidence and provide reliable readouts in ever-compressing time schedules. Now, let's look at the classical hardware design cycle. We have phases like EVT, where we do bring up, and low-level electrical validation, and low-level validation and basic line rate test and port bring up. Followed by DVT, where we do extensive hardware testing, and somewhere through the DVT stage, we clear the gates, and we go ahead with PVT builds. Once all the PVT gates are cleared, we go with MP. Now, this is a classical hardware design cycle, and most of this work is done in collaboration with our partners. Our partners, ODM, do the heavy lifting for the significant amount of testing related to DVT, things like EMC, safety, compliance. All these tests are covered by our ODM partners. Now, in all this, the focus is to test hardware. But there are certain underlying assumptions in this design cycle, because this track is part of a bigger product lifecycle. So let's look at the process again. We have tracks for hardware, which go over traditional EVT, DVT, and PVT phases. We have software and software testing tracks. And all along this, we have manufacturing with its own strict test and processes. Once all these tracks converge, we give a go-ahead for mass production. Now, in this cycle, each track runs independently and has a clear focus of what they want to achieve during validation. When we focus on hardware tracks, the focus is to validate the board. By the time software development and software testing starts, hardware is already a service. Even though you're testing software, for you, hardware is a service, and the the focus point is not hardware. So when we choose to compress timelines in order to move fast by deploying early or building faster, we are trying to compress timelines either in software development or in software testing. Now, when we compress this timeline, what happens is the soak provided by software testing, where hardware is seen as a service and exposes hardware to newer use cases, deployment cases, failures, is less. Now, the shorter this time cycle of testing or DVT or PVT testing, the greater is the risk when you go from deployment into production. So this is a very typical problem at Facebook because of our move fast strategy. So how do we define quality metrics that will give us reliable readout on hardware validation and hardware quality and still keep up the pace? So our problem definition becomes, how do we maintain quality with speed? How do we build a validation pipeline where we leverage our partners' experience in doing hardware validation and bringing up new pieces of hardware, de-risk newer designs against new deployment use cases, and build tests that are repeatable, reusable, and generate reliable results? So let's look at our strategy. We first decided to identify our tests, categorize tests into different categories as to which tests apply in which phase of EVT, DVT, and PVT, see the applicability of automation or manual execution, and find a place in the hardware pipeline. So let's first start with the hardware test categories. There are tests like characterization tests that are typical to EVT phase. What do we want to achieve through characterization? Link stability, bring up stability, clock, power, things like these that are characteristic to the board and last throughout the project. Functional tests, common tests that are common across platforms, things like EEPROM test, BMC functions. Stress tests, which require repeated stress in a single iterations. We want to validate a sensor access on a I2C and I2C endpoint. 1,000 accesses pass, values are reported accurately, stress test. Regression tests, tests that we want repeated over different hardware test phases in the same product lifecycle. Things like reboots, power resets, sensor accesses, and integration tests, which require multiple validations at the same time. The philosophy behind integration tests is during the earliest stages of hardware development, you begin to see your hardware as a system. And you now look at doing multiple validations at the same time. For example, temperature, fan, and power measurements as a function of traffic and load. Non-disruptive upgrade monitoring provided by BMC functions. Link flap test and loopback tests. So how do we extend the hardware cycle? How do we insert this kind of testing into a traditional hardware pipeline? So the approach that we took was to run tests in parallel, along with the heavy lift done by our ODMs. Because we understand our use cases better, we decided to insert automation into this test pipeline. So we started with building EVT automation and running partial automation during EVT phase. Then during DVT, we run first the EVT regression to make sure nothing regressed. And we also built hardware automation tests and start using the DIACs provided by the ODM. And during PVT, we run sampled RDD tests and continuous regression tests. Now, in this model, you're already beginning to see, you're still in design phase, but you're beginning to see your system as an endpoint. You're beginning to see your system as a remote DUT. So once all these gates meet, we go ahead with MP. So some of the results that we noticed were there was a significant reduction in log review. Why? Because there is a clear failure signature in the tests. A test is as useful as an automated test is as useful as the checks you built in. So the clearer the failure signature, the more reliable the test is. Because we are starting to view the system as a remote DUT, and we are not connected to the system, we were forced to build better debug tools in DIAGs. And the way we approached automation as an assistance in execution, rather than replacing execution, we were able to gain execution time in our cycles. So in conclusion, automation is not a replacement, but an extension of execution and analysis. When we define tests, keep deployment perspective in mind and bring it down to the last level of hardware test. Start viewing your test as a remote DUT, which will help you build better debug tools, and explore methods to extend automation deeper into conventional EE validation cycles. Thank you. And now I'll hand it over to Ashik.
Hello. Good morning, everybody. My name is Ashik Ratnani. I'm representing the FBOSS team at Facebook. And today I'll be talking about how we deploy updates for our FBOSS agent software, the service that essentially manages the forwarding tables on FBOSS switches. So let's look at the Facebook's philosophy around deployment. In 2016, we decided to move from a weekly release branch model to a continuous push model. What does that mean? So we started deploying code directly from our trunk, which is also called a dev branch, to production. And we were doing this multiple times a day. The reason behind this was we were able to achieve quicker bug fixes, The engineers were highly motivated to land their changes because they could realize the impact very quickly. And because we were doing frequent releases, we were able to do this quickly because now the amount of changes that are being deployed are smaller and the number of issues that you would hit is much smaller. So we decided to adopt this model for our FBOSS services. Now let's review the risks, right? So FBOSS is a very critical service. A lot of other services would rely on us, which means if we ship a buggy update, a lot of other services would stop functioning and we would have end user impact. If we want to pursue a continuous push model, we will have to do frequent updates. We cannot do an update once a year or twice a year, which means we cannot rely on draining updates because they're very time consuming. And so we have to do non-draining updates. And to do that, we have to use a feature called warm boot. Essentially, warm boot is a feature where FBOSS agent can restart without interrupting the data plane traffic. The ASIC on the switch will keep forwarding traffic while our service restarts. But the way FBOSS agent is set up, the control plane traffic or the slow path traffic has to go through FBOSS agent. So if the service is restarting, that traffic will be interrupted. So let's look at an example where we do an update which is non-disruptive using this model. So for simplicity, I have simplified FBOSS switch into two services, BGP and FBOSS agent. And the bottom two fields represent the state of the switch. So the first thing we have to do is we have to tear down the BGP peerings. Because the control plane is disrupted, we have to initiate graceful restart with our peerings. Once that is done, we can have FBOSS agent go down, which will disrupt the control plane traffic, but you can see the data plane traffic is still going on. The forwarding is still working. At this point, we can update the service. Now, FBOSS agent has to come up, reinitialize back to the original state when it went down, and then BGP can come up and reestablish peerings with its neighbors. So this is a non-disruptive update. But you can see there is a very fine-grained orchestration going on here where services have to come up in a particular order and in a particular time frame because graceful restart itself has its own time constraints. Now let's look at an example where it's disruptive. So again, we tear down BGP peerings. FBOSS agent goes down. We do an update. Now the update was buggy this time, which led to a failed warm boot. And so FBOSS agent couldn't come up for some reason. The data plane traffic got disrupted at this point. And because the neighbors were doing graceful restart, they're still forwarding traffic to us, but we are not forwarding it to other services or switches, which means we are now just black holing this traffic. So basically what I'm trying to get here is warm boot itself is a complicated process where the process of updating can lead to disruption even if you don't have bugs in your own service otherwise. Now, we still wanted to go ahead with the continuous push model. So we decided to figure out how we can mitigate these risks. The first thing we need is to have the code in our trunk to be stable. Without that, we cannot be deploying directly to production. The second thing is we need to ensure during the update, the disruption is limited to a certain threshold. We want to make sure that the impact of the update itself is minimal. So let's look at how we do it. So obviously, how to make trunk stable, you have to do testing. So we have tests, unit tests for our FBOSS agent service, which will validate all behavior for FBOSS agent. We have integration tests that validate the SDK behavior. So this is not the SDK that we write. This is the one that vendor provides us. But we want to make sure that whatever vendor has promised, those functions are working as expected. And we test it on various platforms. And these tests will run on every code commit. So any developer who's committing code has to have these tests to pass. And on top of that, we will also have them run continuously on a hourly basis. This will ensure that if any dependent libraries change and that breaks our software, we will know about that. And anytime these tests fail, an appropriate developer or an on-call will get tasked for it, who can then go and fix it. We also do canarying, which is essentially testing in production. When we test in production, we are deploying completely untested code in production, but we are just doing simple tests like update, restart, and rollback. Now, if we are deploying completely untested code in production, we have to make sure that the user impact is limited. So we select these switches for testing from a non-critical pool of switches. So what do I mean by non-critical? So we select switches that are serving traffic for services that can withstand some temporary outage. And we maintain a pool on a dynamic basis, so this pool keeps getting updated. And so if at all, because of the update, traffic was disrupted, the amount of disruption that the user will experience will be minimal. Again, these tests are also run on an hourly and daily basis, and anytime it fails, we will have an on-call looking at it. So these two types of tests give us enough confidence on our trunk, and we can say for sure if our trunk is healthy or not with a high confidence. Now let's look at how we can limit disruption during the update. So we've built a bunch of monitoring around our deployment infrastructure. We have built some monitors which allow us to catch disruption of different types. So it gives us different signals. So first, we look at server reachability. So if we are updating a rack switch, we want to make sure all the servers behind the rack switch are reachable during the update. This essentially ensures that the data plane forwarding is going on. We also look at neighbor route updates. So if during an update, the neighbors withdraw routes to the switch being updated, that means the GR has not been successful. The graceful restart has not been successful. And finally, we know that after warm boot, the FBOSS agent has to restore its state back to where it was before. So we will capture the snapshot of the switch state before the update, and we will capture it after the update, so we will know if it has restored or recovered or not. These signals allow us to automatically detect the disruption and stop it in time before it goes beyond our control. Now, we limited disruption during the rollout. However, disruption can also happen after the update has been done. And for that, we have broken up our release into multiple phases. And we have bake time in between the phases, which allows us to catch any disruption after the update. So the first phase is the smallest phase, which is 10 devices per hardware platform. After that, we go to 100 devices per hardware platform, which is the second phase. At that point, after that, we do one whole cluster per hardware platform. Now, at this point, we feel confident that the update has been, a lot of switches have been updated, and so we can mark this particular release candidate as production version. And then we go to 10% of the fleet, and then 20%, and the rest of the world. So at this point, our release is complete. So here's what our whole release pipeline looks like. We start from continuous testing. From continuous testing, a particular version gets promoted to continuous canarying. From that point, it gets selected as a release candidate, and then we go through different phases and complete the release. So what have we achieved with this particular approach? Well, we are able to use the same infrastructure to deploy updates to our FBOSS agent and BGP. We use the same testing, same canarying, same phased rollout approach, same monitoring. we are able to do the updates within 2 to 4 weeks, as opposed to vendor switches which take up to 3 to 6 months, mostly because we are doing draining updates there. And we are able to limit the traffic disruption to less than 0.1%, which we feel is low enough to have any end user impact. So in conclusion, we feel that continuous push is the way forward with the way we are scaling in our data center, and if we want to do regular updates to our service. But we are not there yet. We are still 1% finished. We still need a lot. We still need to build a lot of automation around triaging and debugging of issues that are detected by our monitoring. And until we do that, we won't be able to do updates every day. And that would be an ideal situation where we would like to be. So that's how we do deployment for FBOSS. Questions?
If you do have a question, please step up to the microphones. That's so that the presenters can hear you, also so that we can get it on the recording.
Hi. Thank you. So the question, why you need to upgrade so often?
So we feel that if you don't update frequently, then you won't be able to realize the impact of your work that you have done as engineers immediately. And we have, in Facebook, the philosophy is to move fast, and this allows us to move fast.
Are we talking about features or?
This is any features, bug fixes, any code commit that you do.
Okay, thank you.
Your non-critical pool, what are those devices doing that make it non-critical?
So they are serving traffic to services that can handle temporary outage. So certain services can have maybe stateless or may have enough redundancy that they can take a hit. And if the whole rack is built of the same type of services which can absorb that temporary outage, we consider that as safe.
Okay, and then a question, as you're developing software for validating the hardware, you mentioned that you're using your ODM's SDKs. Mm-hmm. At that point, are you only engaged with one ODM? And when you bring on someone else, the whole cycle starts all over again?
At this point, the effort is to abstract it as much as possible. Because we know what the functions we expect from our hardware, we are trying to write tests that are independent of the ODM SDKs. I want to access firmware versions. I want to test route scale. I want to test simple things like fan speed control. Things that are in my control, our control is what we are trying to build tests for.
So does that mean in your flow you could handle 2 ODMs in parallel?
Yes.
Okay, thank you.
That's the effort.
Going back to the first question, what are the kinds of things that you would be updating in the code for FBOSS on a regular basis?
There will be features, there will be bug fixes, there will be normal requests, enhancement requests that we get from our partner teams.
Yeah, I was wondering, do they fall into a particular area though, type of capability or anything, or are they just sort of across the board?
Just across the board.
So I have a question. Can you give us an idea of how long of time it takes from when a engineer makes a commit until it's in full production?
So as I said, the whole release takes up to 2 to 4 weeks. So you can expect it from any time between 2 to 4 weeks to get it into production. And since we pick it from the dev branch itself, whatever is in the dev branch, top of the trunk, as long as it's healthy based on our testing, we'll pick that release and ship it.
About your approximate EVT, DVD, PVT?
Speak closer to the mic, please.
What's your average duration of your EVT, DVD, PVT, and how much you were able to shrink that based on that optimization you made?
So it really depends on the number of issues that are found during EVT, DVT, and PVT. But we decide based on the availability and the criticality of that issue. Like, based on the kind of issues we're seeing, we want to assess how relevant it is in deciding or affecting the availability of that platform once it is in hardware, once it is in deployment stage. So based on that, we choose to extend or compress the cycle. But given the existing size, say 12 months, if the end-to-end cycle is 12 months, depending on issues, it can be more or less. But if it's an issue that will cause an outage eventually in the field, that becomes a critical issue and will cause an extension of timeline. But as such, we do not track based on time, we track based on the gates at each stage.
Okay, thank you, Facebook.
Thank you.
Thank you.